Sample test. Now we're on to number 9. How many distinguishable permutations are there of the letters of each word? House. H-O-U-S-E. No repeats, so we got 5 choices times 4 choices times 3 times 2 times 1, or 5 factorial, which is 120. B, housekeeper, a bookkeeper. Bookkeeper, so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters. So that's going to be 10 factorial, 10 for the first, second, third, fourth. But we have some duplicates. And if you remember, when you got duplicates, you got to divide out that in factorial. There are not 2 B's, so don't worry about it. There's only 1. There are 2 O's, so you got 2 factorial. There are 2 K's. There are 3 E's. There is only 1 P and 1 R. So you would have to work that out. And I presume that you can do that. This is 2, that's 2, that's 6. 2 times 2 is 4, times 6 is 24. So you got 10 factorial divided by 24. 10 math probability factorial divided by 24 is 151200. 10. How many ways are there to select 3 representatives from a group of 200? So we're just selecting 3. We're not arranging them into positions or offices or some kind of arrangement in chairs or something. Or so we're just got from 200. We're picking 3, C3. So that's going to be 200 factorial over 200 minus 3, 197 factorial, 3 factorial. That's what C is. And so that's 200 times 199 times 198 times 197 factorial. The 197 factorial is going to cancel. And then 3 factorial. So we're going to have 200 times 199 times 198 divided by 3 times 2 times 1, or 6. So you can work that one out. I'm not going to, well, I'll do it on the calculator. 200 math combination 3, and that's 1,313,400. 1,313,400. 11. How many ways are there to select a president, vice president, and secretary from that? So now we do care what order they are. So that's 200 P3. So this is gone. It's going to be 200 times 199 times 198. We can do this in the calculator by doing same thing, only I got to change this to NPR. Math probability NPR 3, and I get more of them because it's 6 times this number, which is 7,880,400. So that was 11. 12. The table includes flight safety information, and this should have been in hours. Down here in hours. I was thinking miles when I wrote the test, so down here these two should be hours. Determine the fatality rate in fatalities per 100,000 hours flown in 2008. Fatalities 494. In hours flown 22.8 million, which is 22,800,000. And then we're supposed to figure it in 100,000 miles flown. 5 zeros cancel 5 zeros and when you're doing that, and so we get 494 divided by 228, which is 2.1617 rounded per 100,000 hours flown. .17 fatalities for every 100,000 hours. That's A for 12, and B, determine the accident rate in 100,000 hours for 2006. So that's 706 over 24 million. So we're going to be able to do that, and this is per 100,000. It's 5 zeros, cancel 5 zeros, so that's 706 divided by 240, and that's 2.9 per 100,000 hours flown. So you were better off in 2008 than in 2006. Gotten better. All right, that's number 12. Now we're going to move on to 13, and it says, discuss how the law of large numbers can lead to faulty reasoning of the gambler's fallacy. Well, people say, like flipping a coin, you should get closer and closer to 50-50. That's what the law of large numbers. But if you happen to start with an unusually bad streak and get a whole bunch of tails to start with, and so you're down, let's say you only got 40% heads, and you were going for heads, so you haven't been lucky, then the probability for the rest is 50-50, and so you're going to be down those all the way through. Even though the law of large numbers says the rest of these should be close to 50-50. So that leads people to think, okay, I'm going to even out here, but it doesn't have to. The next one is always a 50-50. And 14. Give the probability distribution for the number of heads when flipping 4 fair coins. Well, you got heads, tails, then so the heads, tails, heads, tails, and then heads, tails, heads, tails, heads, tails, and heads, tails, and then again. And so 2, 4, 8, 16 outcomes. And so the probabilities are all going to be out of 16. And it says the probability of heads. So we're either going to get 4 heads, or 3 heads, or 2 heads, or 1 head, or no heads. The probability of all 4 heads is only 1 branch in this tree diagram. The no heads is all tails, which is only 1 branch out of those 16. The probability of 3 heads means there has to be 1 tail, and the tail can be on the first coin and then all heads, or in the second coin and all the rest are heads, or on the third coin and all the rest are heads, or on the fourth coin. There's only 4 ways to get 3 heads out of the 16. Of course, if there's 4 ways to get 3 heads and 1 tail, means you have to get 1 tail, the same as getting 1 head, so there's going to be 4 ways out of 16. And what's left, getting 2, happens the rest of the ways. 1 plus 4 plus 4 plus 1 is 10/16. So there's 6 more out of the 16 for there. So there's a probability distribution of heads flipping 4 fair coins. Fair meaning 50-50 chance. Okay, that's it.